Okay, so we've got lesson 83. It's page 518 and it's called Vectors in 3D. So to use vectors in 3 dimensions, three-dimensional problems, we use 3 perpendicular axes, the x, y and z axes. If we draw the x and y axes as usual, so I'll do those here. This actually might be better with squared paper. I'll try and do it here. If I need to, I'll use squared paper in a moment. Okay, and the convention is to draw the z-axis coming out of the page. So if the page is lying on the desk, so that's the x and y, like we would normally have them. And then this is the z. So the positive, so if the page was laying on the desk, so you'd have, that way we'd have y up there. If we tipped it over, x up there, and z up there. Okay? If the page is lying on the desk, the positive z-axis points towards the ceiling. Axes like these are a right-handed set because you can position your thumb, forefinger and second finger in the direction of the x, y and z axes respectively. Okay, I'm going to rub this one out because I want this other one for my next diagram. So a vector R in 3D has 3 components. So let's put this over here somewhere. How about there? Okay. Hopefully you can see this in 3D in a minute. We can write it as a column vector or use I, J and K, which are the unit vectors of the x, y and z directions. For example, diagram to show R as a column vector in component form and as a 3D diagram with OP as a right-handed set. Right, so there's O to P. Okay, so if we drop this down here and then draw this way and draw this one this way, draw this back the same as what we did on that lower line, that one there. This one comes across to here, this one goes to there, this one goes back to there, this one goes to there. I think you can see that, that's not too bad for a free hand. Okay, so what we've got is it's that far in the x's, it's that far up in the y, and it's that far up in the z's. So they're the 3 dimensions. So this is R, this is the vector that takes us from O to P. The magnitude or modulus of R is mod R, which is the length of OP in the diagram. Okay, I think I've got everything we need there. All these are at right angles to each other. Okay, the axes, that's in the diagram, sort of. Yeah, okay. So conventionally we'd say the x, the y, then the z. So we'd say do the x first, then the y, and then the z. You can see that because it brings it away. But whichever way around you do it, you'll always arrive at P. Okay, using Pythagoras, we have the magnitude of vector R, which is AI, sorry. This is A, that length there. The Y is B, and the Z is C. So it's AI. I is one that direction, J is the unit in that direction, and Z is one in that direction. BJ plus CK, the modulus of R, is the square root of A squared plus B squared plus C squared. So it's just like Pythagoras, which we had already in 2D. You extend it with this third component there. The direction of R makes angle alpha with the positive x-axis. Let's think about this. Beta with the positive y-axis. And gamma with a positive z-axis. It's quite hard to draw this in. That's the angle alpha there. Beta is there. And gamma is that one there. Just that looks more like an alpha, gamma. It's a bit hard to draw this in 3D. Okay, cos of alpha is A over the modulus of root R. Let's see how I can draw that in that diagram. Or should we just say that that's a rule? You can actually see it with any of them very well at all. Just thinking about that one, how to show that with a diagram. I'll do a new colour. It's a bit hard to see this in 3D. Let's go for blue. I haven't used blue yet. So if we do this line here, where the right angle is A cos alpha equals R. The right angle is, what do we say? Cos R cos alpha. Oh, I've got my diagram, so I'm looking at the one in the book now. Yeah, just accept that as a rule for now. Or look in the book. The diagram's slightly different in the book. I don't know if it's easier to see these here. But yeah, I'm just going to put those in purple. Something to come back to. Have a little think about. It's hard to see with a diagram. I don't want to give up on it. So what we've got R cos alpha equals A. So that is... Oh, I did practice this before. I just didn't spot that this was coming. Right, that's the A there. We've got the R up here. R, there's the alpha. R cos alpha equals A. So that means that that's the right angle there. So it means that there's a right angle between A, that's P there, that's, if you like, A there. So there's a right angle that goes from A to P. So there's a right angle in there. It's hard to draw it. Okay, the next one, R cos beta equals B. That one's a bit easier to see, I think. That one, there's a right angle there. So if you like, cos beta equals B over mod R. So this means that R cos beta equals B. So that's the hypotenuse, that's the cosine, that's the adjacent. So the hypotenuse is the long one there. It's just hard to see these right angles. The last one, cos gamma equals C over mod R. Mod R cos gamma equals C. So again, that's the hypotenuse. And that's going to be cosine, that's going to be the adjacent. There's the adjacent. The right angle there for that one. Yeah. you don't have to draw this diagram ever. Okay, sorry, I've drifted a little bit there, thinking about it. I did practice this yesterday and it seems to go okay, so there's something. Have a look in the book as well and ask me if you get stuck, if you need that one. So, anyway, if we square each of these in here, cos squared alpha plus cos squared beta plus cos squared gamma, so it's a squared over modulus of r squared, b squared over modulus of r squared, c squared over modulus of r squared, and then they're all over modulus of r squared, and a squared plus b squared plus c squared is modulus of r squared, so that's 1. Okay. Right, let's go into some examples. That diagram was a bit hard, set my eyes funny. The position vector of a point A defines its position in relation to an origin O. The position vector of a point A is O to A, and you usually write this as A. For points A and B, A to B is A to O plus O to B, which is equals to O to B minus O to A, which is B minus A. We've seen this before. You've got to go from A to B. A's there, B's there, there's the origin. If we want to go from A to B, we've got to go back from A to O. So it's minus O to A plus O to B. So it's minus A plus B, which we write as B minus A. Right, example 1. Points A and B are position vectors. A, there's that one, B is that one. Work out the length of AB. So the modulus of A to B is the size of vector B minus A. They didn't need to be as long as that, those lines. And B is 4, 0, minus 7. And A is 3, 2, minus 5. So it's 1, minus 2, minus 2. And so then we want the size of all these. So the size of this is going to be the square root of 1 squared plus minus 2 squared plus minus 2 squared. So it's root 9, which is 3. The angle between AB and the y direction, showing your working. Okay, so we've got the angle between A to B and the y direction, it's showing your working. So we need this here. It's cos of the angle is the y component divided by the modulus of the angle. So cos of beta, the y one is minus 2, divided by the size, which is 3. So beta is cos inverse minus 2/3, which will come up on your calculator as 131.8 degrees. And C, the unit vector in the direction of A to B, well, that one is 1/3 of 1 minus 2 minus 2. So those answers have come from this first one here. That's the vector that goes from A to B, and that's got modulus 9, square root of 9, which is 3. So for the unit vector, we've got to divide this by 3. So if you can you can say it's 1/3 I minus 2/3 J minus 2/3 K. Okay. Example 2. Points P and Q have got those position vectors. The point R lies on PQ such that P to R and R to Q is 2 to 3. So P, R, Q, and that's twice, that's 3 units. And let's get the origin there. You can put the origin wherever you like. Right, so work out the position vector of O to R. So we want to know what that is. we know what P is, and we can work out what P to R is, because it's along the line of P to Q. Right, so let's start by working out P to R it's going to be 2/5 of P to Q. Okay, and that's because there's 2, and this total length is 3, so it's 2 out of the 5. So this is going to be 2/5 of Q minus P, which is 7, 4 minus 4, minus 3, minus 3, minus 1. PQ is Q minus P, which is 7, 4, minus 4, minus 3, minus 3, 1. And then I've put that into there. So it's 2/5 of 10, 7, minus 5. So that's going to be 4. 2/5 of 7 is 14 divided by 5, which is 2.8. 2/5 of minus 5 is minus 2. Okay, we actually want O to R, so that's going to be O to P plus P to R. O to P is minus 3, 1. P to R is 4, 2.8, minus 2. 1 minus 0.2 minus 1. Okay, that's that one there. Just check the answer there. Yep, got the same answer there. Example 3. This is the last one. A, B, C, D have position vectors A, which is 1, 1, minus 2. B, which is 3, 5, 4. C, minus 1, 7, minus 2. Oops, won't put that C there, let's put it around here. And then D, 7, minus 3, 6. Okay, notice I've gone round in anti-clockwise order. That's quite traditional to do that one. P, Q, R and S are the midpoints of AB. Q is the midpoint of B to D. How have they done this? Right, it's quite traditional to go around anti-clockwise, but they haven't done it this time. Right, now I'm just going to change these round. A, B, put C over there, minus 1, 7, minus 2. D over here, 7, minus 3, 6. BD is Q. C to D is R, and S is A to C. Show that PQRS is a parallelogram. Well, I haven't drawn it in any way to scale, but we've got to use the numbers. So it's not quite a parallelogram the way I've drawn it, but we'll see that it is. So if it's a parallelogram, then PQ will be equals to SR, and PS will be equals to QR. So that one will be equals to that one, and those two will be equals. Okay, so we've got some sort of origin here. Right, O to P is O to A plus a half A to B. So it's 1, 1 minus 2 plus a half of, if you remember, A to B is B minus A, so it's 3, 5, 4, minus 1, minus 1, minus 2. 1 plus a half of 2 is 2. 1 plus a half of 4 is 3. And then minus 2 plus a half of 6 is 1. So that's O to P. Okay. To do the same for just thinking I've got to do then O to Q, O to S, O to R, and then do P to Q, S to R. There's a lot of vectors going to be on this page here. Q. I think I've got to do it. O to Q is O to B plus a half B to D. O to B, 3, 5, 4, a half of D minus B, 7, minus 3, 6, minus 3, minus 5, minus 4. So 3 plus a half of 2, 3 plus a half of 4, 3 plus 2, 5, 5 minus 4, 1, 4 plus 1, 5. So that one is 2, 3, 1. Let's do these in a different colour. That one is 2, 3, 1. That is 5, 1, 5. I might be able to put some of the numbers on the diagram. Right, O to R next. We'll do that as O to C plus a half C to D. O to C, minus 1, 7, minus 2, plus a half of C to D, which is D minus C. So it's 7 minus 3, 6, minus 1, 7, minus 2. Minus 1 plus a half of 8 is 3. 7 plus a half of minus 10 is 2. Minus 2 plus a half of 8. Minus 2 plus 4 is 2. Let's go from the blue. So O to R, 3, 2, 2. And then that next one, O to S. I'm going to do that as O to A plus a half, A to C. O to A, 1, 1, minus 2 plus a half. C is minus 1, 7, minus 2. Then minus A, which is 1, 1, minus 2. 1 plus a half of minus 2 is a 0. 1 plus a half of 6 is 3. Minus 2 plus a half of nothing is minus 2. Right, so providing I made any errors. Okay, so I need to look at the vector going this way. That one there, P to Q, that's got to go, I'll do these by the side actually. So once you've got all these, you can come up here, P to Q. So it's 5, 1, 5, minus 2, minus 3, minus 1, 3, minus 2, 4. S to R is hopefully the same as P to Q. S to R, 3, 2, 2, minus 0, minus 3. Then 2 minus 2. There's a mistake. This last one here, that one's wrong there. Let me explain why. One, the middle one, 1 plus a half of 6 is 1 plus 3, which is 4. So that means S has got a 4 in the middle there. So that means S, that one there needs to be a 4. And look, Perfect. 3 minus 2, 4. So S to R, that one is the same as that one. So halfway there. So now if I can just show that that one is the same as that one, then we've got a parallelogram. So next thing we need to do is a P to S. Just got to be an S minus a P. 0, 4, minus 2, 2, 3, 1. Minus 2, 1, minus 3. And then we want a Q to R. R minus Q. 3, 2, 2. Minus the Q, 5, 1, 5. Minus 2, 1, minus 3. Yes, that one does equals to that one. Hence we have a parallelogram. Parallelogram. Because the sides are the same vectors. I've done that one.